Hey team, Dr. Jack Gordy here, and in the previous few videos I've covered what is a p-value, what is a test statistic, what is the null hypothesis, and what is the z-score and a t-score, and how do we calculate p-values from this. Now, often in research, we don't just have two groups, which is what we use for a t-test for comparing two groups. Are they statistically significant? Quite often we have 3, 4, 5 groups in our experiments. How the heck do you analyze that? And this is when the ANOVA comes in. And so in this video, I'm going to explain what an ANOVA is and how it works. So let's jump into it. First of all, what does ANOVA even mean? Well, it means analysis of variance, and that gives you a little hint about how it works. So ANOVA is just short for analysis of variance. So let's jump into it. Here we've got our three groups here. Now let's do a little bit of statistical anatomy to describe what we're looking at right here. So first of all, on the y-axis, we have a dependent variable. Now, the dependent variable depends on the x-axis, which is the explanatory variable. So if we have a little think about what that might mean is, let's say this is blood pressure, for example, some sort of quantification of blood pressure. Blood pressure could depend on the placebo, the drug, low drug dose, or high drug dose. So if the drug interferes with blood pressure, the blood pressure depends on the drug. And so the drug is explaining the variation in the dependent variable. So this is an explanatory variable which might explain your results on the y-axis. So we always call this the explanatory variable and this the dependent variable, because it depends on the variable that's explaining it. This explains the results you're getting on the y-axis. So what is a p-value? Let's just do a quick refresher on that. It's the probability of getting a test statistic as or more extreme as the one obtained given the null hypothesis is true. And what's a test statistic? Well, a test statistic is a single number that it turns all your data and your research question into a single number. Now, the ANOVA is crazy. It's like, how do you get all of that data into a single number? So let's have a look at some examples of test statistics. We've got a z-score, we've covered that, a t-score, we've covered that, an F ratio, a Mann-Whitney U, and a chi-squared. So what test statistic does the ANOVA use? It uses the F ratio. So I'm going to go into how to calculate the F ratio and what actually is it. Now, it's quite an amazing thing, the F ratio. How do you get all this information into a single number? How do you turn the numbers in each group, the variation of each group, the means of each group? How do you turn that when you might have 3 or 4 or 5 groups? How do you turn all of that information into a single number so we can run a statistical test on it? Well, let me explain that to you. Here we go. So we've got our data here. We've got our dependent variable and our explanatory variable, and we've got each little group here in the data. Now, what you can see is the data is actually quite tight. It's not variable around each mean here. So this is in a tight little group. This is in a tight little group. This is in a tight little group. There's not a lot of variation in this data. But what happens if we take that data and we just lump it all together? So we don't break it up by our explanatory variable, and we now group it all together. So this is A, B, and C on a single plot. Here you can see each data point has just come across here, over here, and it's color coded for you. Now, what's happened to the variation? We've now got massive variation when we combine our data. And I'm using this term variation a lot, which gives you a little hint about what we're going to do, because an ANOVA is an analysis of variance. So we've got big variation when we combine our data, but when we take into account our explanatory variable over here, which are our treatment groups, our x-axis, we have little variation. So let's just look at that variation here. We've got little variation when we include our explanatory variable, and when we get rid of our explanatory variable and lump all the data together, we have big variation. So what we call it, and this is a key statistical point, and going forward into any stats, if you go any higher than what we're doing right now, ANOVA, these principles are the key principles. You could forget about t-test, you could forget about ANOVA. If you understand these principles, you kind of get statistics. So in when we included our explanatory variable, there was still some variation left over. So when we broke the data up into our groups, there was still a little bit of variation left over. So that variation is unexplained. We don't know what is causing that little variation there. However, we saw the big variation when we lumped our data together shrink massively when we broke our data up by our explanatory variable. So that variation is explained. We've explained why this data was variable when we lumped it together, and it's because it actually belonged to two different groups. So once we overlaid our explanatory variable, the variation shrunk. So our explanatory variable explained a lot of variation. Now you can see why we call it an explanatory variable. It explained a lot of the variation. Now the F ratio is really just the ratio of the explained variation against the unexplained variation. So here we can see we've got a big explained variation and a small unexplained variation. So this number might come out as something like 2.5. This number's 2.5 times bigger than this number. So now we need to put that onto an F distribution. This is the F distribution here. Now you can kind of see it looks a little bit like a normal distribution here, but it's a bit squashed. And that's because you can't get a negative ratio, right? You can't divide two positive numbers and get a negative number. So we can't get this normal distribution going off down here. So it looks like a bit of a squashed normal distribution here. And all we need to do is look at what proportion of this curve is as or more extreme as 2.5. So we take the shaded area and we divide it by the total area under the curve, and we will get our p-value. And that p-value is much, much lower than 0.05. So we have a significant effect. So we will now say our explanatory variable explained a significant amount of variation in the data, which is really cool. And that's the answer to the ANOVA. Now, much like the T distribution, the F distribution changes on your N. It's a little bit different because it kind of gets squatter and fatter as you increase the N. And that's because you always explain a little bit of variation if you break the data up into smaller and smaller groups, but that's purely by chance. So you need to get a bigger F value as your N goes up. But that's beside the point. The point is that the F distribution changes as you change the N, and it kind of gets a bit squatter and fatter as you increase the N. Now let's look, I showed you a significant example. Let's look at an insignificant example. So here we have our dependent variable and we've got our data A, B, and C. So this might be drug, placebo, low drug, high drug. And you can see we've got big variation there. We've got lots of variation in the data. Now, if we combine this data into a single graph, so we lump all that data together, we get rid of our explanatory variable down here and just lump all the data together. Here's our data here, and we can see we've got big variation. Now let's compare these variations here. So we combine them. Now we look for our explained versus unexplained variation to get our F ratio, and what you can see that there's no explained variation. When we broke the data up into our groups, it was as variable as when we grouped all the data together. So there's no explained variation. Unexplained variation is massive, right? Because it's that leftover variation once we've overlaid our explanatory model. So you can see here we've got a small numerator, a large denominator. We're going to get a small F ratio over here. So we're going to have a huge proportion as or more extreme as this value here. So our p-value is going to be massively not significant. So, I mean, you can kind of just crudely see it as very variable here, very variable here. Our explanatory variable has not explained the variation. It hasn't explained a significant amount of variation. If you look at this, when we break the data up into our explanatory variable groups, you can see that the variation has gone from big to small. That is what an ANOVA is doing, but it's actually what all statistical models are doing. So what have I told you? This works for linear models too. So let's have a look at a linear model. This time we've got a dependent variable, and this time we have a continuous explanatory variable. So it's not groups, it's not A, B, and C, it's actually numerical. So an example might be coolness rating on a continuous scale between 0 and 10, let's say, and knowledge of immunologist. I'm an immunologist, by the way, so I might have biased this example. And as you can see, as your knowledge of immunology increases, so does your coolness. Isn't that awesome? And this is a continuous variable right here. we will call it. Now, what you can see is instead of looking at the distance between the data and the mean, which is what we do to calculate sort of the standard deviation or the variance, we can look at the distance between each data point and that linear regression that we ran through it, that sort of line that predicts the shape of that curve there going on, that linear model. And so these lines here sort of represent the variation, and we can sort of take the average of that roughly. And we can see that there's not a lot of variation around that line. The dots are tightly scattered around that line. But if we get rid of our explanatory variable, which is our knowledge of immunology, and we combine it all together, here's our data here. Each one of those corresponds to one of those. And you can see that we've got big variation here. So now when we compare these two, little variation versus big variation, we've got a very small amount of unexplained variation in coolness, and that's because coolness is really tightly related to your knowledge of immunology. And then we have a huge amount of explained variation. The variation shrunk massively once we incorporated the explanatory variable of knowledge of immunology into our data analysis. So then we can draw an F ratio there and come up with a significant p-value. But what if I told you everything is virtually a linear model? And this is one of the amazing things that we learn about statistics. Worrying about t-tests, worrying about ANOVAs, two-way ANOVAs, one-way ANOVAs, ANCOVAs, multiple regression. It's all a bit silly because it's all exactly the same thing. You overlay a model and then you look at the explained versus the unexplained variation and you derive your p-value from that, okay? And that's a key principle, and I'm going to cover this in the next few videos about statistics. Don't worry about t-test versus ANOVA versus this versus that. Just think about stats as overlaying a model and looking at the explained versus unexplained variation, because it all works out to be the same thing. And so it's very similar to this meme here. Wait, it's all been a cake. It always has been. It was very popular a wee while ago, where everything turned out to be cakes, keyboards and anything, Coke bottles, everything turned out to be made of a cake. It was a brilliant time on Twitter. Things were simpler back then. I wish I could go back to that time. So up next, I'm going to actually jump into how we do some of these models you speak of, and I'm going to use this free statistical software called Jamovi. So if you want to follow along, I really recommend you go and download this free statistical software called Jamovi, and we will run through how to do some of these statistical tests I've been talking about and how to actually deal with data now that we've got a deep understanding of how data works. Thanks, team.